My talk will be focused on understanding the microstructural origins of an enhanced resistance to hydrogen-resistant fatigue crack growth in an Ausformed and tempered martensitic steel. I think pretty much everyone here understands the importance of pipeline steels and hydrogen transport in pipeline steels. In this context, there was an empirical study which showed that when the tensile strength was lower than greater than 900 megapascals, then the relative fatigue crack growth had a frequency dependence. For example, if you look here, this is SCM 440 tempered at three different temperatures, 550, 600, and 650. For the case of 550, the tensile strength is greater than 1000. And we can see that as there is a change in the loading frequency from 1 to 0.1, there's an order of magnitude difference in the relative fatigue crack growth. This is obviously not desirable. And what is ideally required is a cycle dependence rather than a frequency dependence. And this we can refer to as a 900 megapascal barrier. However, recently, Professor Matsunaga's group found like a couple of steels, same composition, but with Ausforming, they were able to breach this 900 megapascal barrier. And we can clearly see that there is no frequency dependence, even though the tensile strength is much greater. So the previous steels were tempered materials, which will be referred to as T, and the ones with enhanced properties are Ausformed materials, where there is an Ausforming about 50% compression, which is essentially like the sample has been taken out, and with a thermocouple, the surface temperature is measured, and then there is a 50% compression, and after that, again the typical tempering process. When we look at the phase diagram, what we see is there's a lot of carbides which form at temperatures lower than like 750 or 800. So we confirmed it with TTT curves that for whatever the temperature of Ausforming, we do not have any primary carbide precipitation. So if we want to understand the effect of carbide, we need two things. The first is the microstructure, and how Ausforming changed the microstructure. And the second is the effect of this microstructure on the hydrogen-assisted fatigue crack growth. In the microstructure, a few changes are pyrosinate grain boundary morphology, the pyrosinate grain boundary segregation. We have the lattice size and morphology, carbide structure and chemistry, carbide size and distribution. Now, these affect one, the pyrosinate grain boundary cohesive strength, hydrogen permeability, hydrogen trapping ability, and fatigue crack path. So the PGB morphology can directly influence the fatigue crack path. The pyrosinate grain boundary segregation affects the fatigue crack path as well as the cohesive strength. The lattice size, we expect it to affect the fatigue crack path. The carbide structure, chemistry, size, and distribution will affect all four components. So in the talk, first we will look at or we'll try to determine how this hydrogen-assisted fatigue crack growth is in the Ausformed material, and then we'll go back to the microstructural features and see what is the smoking gun or what is causing this. So this is for the purely tempered materials, by Dr. Chen. And if we look at this condition where we have a frequency of 1 Hertz, and the pyrosinate grain boundary fraction is about 45 to 50%. However, we have a samples from Professor Matsunaga's group after performing these CT specimens in 90 megapascal hydrogen. And when we look at frequency of 1 Hertz, what we observed was something very interesting, that when we look at, this is the pyrosinate grain boundary, and this is the fatigue crack growth. And we realize that when we look at, when we observe a total crack length of about 126 microns, only 5% of this total fatigue crack growth was about pyrosinate grain boundary. So this is predominantly intergranular. And we also try to look if there is any specific crystallographic mode. Occasionally we saw some 110, but there were many areas, for example, here where it was completely trans-lat growth. However, there was no specific crystallographic cleavage plane associated with this. We'll come back to it probably at the end. The fractography also shows the same story. This is for the T600, we see some intergranular features. However, in AFT's materials, we have no intergranular cracking. So we realize that there's a change in the fatigue crack path, and this also means there's a change in the causal strength of the pyroxene part. Now, the next thing which we want to look at is hydrogen permeation tests. And this is the standard electrochemical permeation, and we have the hydrogen diffusing, and we have nickel plating on the other side. There are different methods of calculating. We chose the time lag method, where it is we look at the corresponding time for 0.63 times of I stable current. The thickness of both the materials were very similar. And what we realized is that the diffusion coefficients of AFT is slightly lower, but 4 to 6. We wouldn't call this a significant difference in the context of hydrogen permeation. For example, if you look at literature, of course, this is for different alloying elements. We see very clearly that in some cases, some carbides very drastically shift the breakthrough time and change the diffusivity. So in our case, we can safely assume that the effect of Ausforming on the hydrogen permeability is negligible. We are yet to perform hydrogen TDS studies to look at hydrogen trapping ability. But now we want to go back and see how the microstructure is affecting this. So this is IQ plus idea, and this is the corresponding SE image. And we reconstructed the pyroxenite grain boundaries in OM. We can clearly see these pyroxenite grain boundaries also in the SE image. And when we look closer, what we observe is the coverage of carbides on the pyroxenite grain boundary is nearly 100%. We can look at a different area as well, and we will realize the same thing, that we have nice coverage of these carbides on the pyroxenite grain boundaries. Now, the question is, why is this important? So this is the same. We'll come to it in a couple of slides. But now when we look at AFT 600, this is, so we looked at this corner where it does not have any influence with this crack propagation. So we consider this as undeformed state. We can clearly see that we have this nice pyroxenite grain boundary. But very interestingly, we start seeing these small grains. I'm not sure if you see. We ideally don't expect this because the Ausforming temperature is much lower than the recrystallization temperature. One hypothesis is the temperature which we measure before Ausforming is on the surface using the thermocouple. It is likely that at the center of the specimen, the temperature is much higher and we see some recrystallization happening. Now, on the transverse direction, we see this pancake morphology. Again, we see these small grains suggesting some recrystallization. However, what was very interesting for us in Ausformed 600 material is this is a pyroxenite grain boundary. But now when we look at the carbide precipitation along this pyroxenite grain boundary, the coverage is much lower. Again, and now why is this important? We look at this same material, but now the frequency is about 0.010 to the power minus 3 hertz. And we made a TEM lift out at the edge of this fatigue crack curve so that we can capture the fatigue crack in the lamella. So what we see is this is the beginning of milling, and this is after thinning the lamella. We can see this is the crack, which is, so the crack propagation direction is into the lamella. And so this is again showing some STEM images. We performed some TKD. The resolution of TKD would be about 8 nanometers. So this is the 10 nanometer step size. And this is 25 nanometers. The reason we went a bit to 25 is, if you see here, this crack is slightly curved. This is coming because of drift, because of the smaller step size. So when we went to a little larger step size, we can clearly see that the crack is quite straight. Here we have this crack which is propagating along the block boundaries. There's this very interesting feature here, which is transgranular crack propagation. And when we also, we see these are translap cracks where we cannot exactly determine with a TKD whether this is 100 or 110, because it could be either of these based on the trace analysis. Now, when we look at EDS, we have these chromium-rich carbides. And this is the area I was talking about a couple of slides ago, which is an area where there is block boundaries, but this intersection is actually a translat crack. And when we look at it, we clearly see there's a carbide, and this carbide is having a decohesion at the boundary. However, like this is a smoking gun for us that when we have this carbides at the pair-Ausformed grain boundaries, these also would enhance the decohesion in the presence of hydrogen. And this was also previously reported that because of Ausforming, the carbide density at these pair-Ausformed grain boundaries reduces, and that is also what we observe here. Now, 2 minutes. Okay. So the other things but we also have a few challenges. Firstly, in some areas, we find it very difficult to determine what exactly is the pair-Austin grain bond in the Ausformed material. And in some cases, we see these lats which are about 120 or 150 micrometers length. The pair-Austin grain boundary size is not this big. This might happen probably because during Ausforming, we are causing only one variant to be selected. The pair-Austin grain boundary segregation is we are yet to do it based on APT studies. Just to summarize, we have in Ausformed material, the pair-Austin grain model cracking was suppressed. The smoking gun at this moment is the carbides at these boundaries, and the coverage of these carbides is much lower in the Ausformed material.